In Lesson 1, we'll introduce the three types of basic near numbers: finite, infinite, and constant. Then we'll talk about what we mean by slices of near numbers. This will set the stage for all that follows. Let's start by talking about numbers. Every now and then in our mathematical careers, a new type of number comes along. We start with the counting numbers 1, 2, 3, etc. Eventually we see rational numbers as fractions, zero and negative numbers, then powers and roots and transcendental numbers like pi and e. All of these numbers live on the real line, and they share a common feature. Each one sits still at a fixed position. Calculus is fundamentally concerned with motion and change. So when we step into this realm, fixed numbers are no longer enough to properly express the concepts we need to understand. We need a new type of object that embraces this motion, rather than forcing us to constantly talk around it. We call these objects near numbers. Near numbers are objects in the real line that squeeze forever nearer to some location, providing the language we need to accurately express the concepts of calculus. There are three types of basic near numbers. Let's look at the number 0 on the real line. There are locations near 0 that we'd like to get a grip on, for instance, just to the right of 0 or just to the left of 0. It's a quick argument to show that no number accurately expresses these locations. For example, let's look at just to the right of 0, which we could errantly phrase as the number just to the right of 0, or the smallest positive number. Well, for any positive number x we choose, if we zoom in enough, we see that there's a gap left between it and 0, so it isn't just to the right of 0. Also, 1/10 of x is an even smaller positive number, so x isn't the smallest positive number. No numbers work to express this concept, so we need a different object that's not a number. This leads us to the basic finite near numbers. The concept of just to the right of 0 is expressed by the near number 0 plus, which squeezes forever closer to 0 from the right side, not including 0 itself. In this way, it's eventually smaller than any positive number. There's nothing special about 0 here. We can squeeze toward any real number a in the same way, giving us the near number a plus. Similarly, a minus squeezes forever nearer to a from the left side, not including a. We can think of the number a itself as a near number by optionally putting a little dot on it. This is a on the dot, and it doesn't squeeze at all. These three adornments, plus, minus, and dot, can be combined in any way we like. A plus dot squeezes towards a from the right side but does include a. Similarly, a minus dot squeezes in from the left and includes a. Putting all three together, we have a plus minus dot, which squeezes towards a from both sides and includes a. Finally, a plus minus squeezes towards a from both sides but does not include a itself. It might seem at first like nitpicking to clearly distinguish these different ways of squeezing on the real line, but precision and clarity are essential to getting calculus right. These basic finite near numbers are our models for what we call convergence, which means squeezing closer and closer to some real number. Other important locations on the real line include way off to the left and way off to the right, often invoking the word infinity. It's again a quick argument to show that no number accurately expresses these locations. Take for example way off to the right, which we might errantly call the number infinity or the biggest number. Well, for any positive number x we choose, if we zoom out enough, we see that it's not actually all the way to the right as infinity should be. Also, 10x is an even larger positive number, so x isn't the largest number. No numbers work, so we again need a different object that's not a number. This leads us to the three basic infinite near numbers, each of which pushes, in its own way, farther and farther to the ends of the real line. Positive infinity looks like an interval that extends all the way to the right, and its left end pushes forever farther rightward, making it eventually larger than any positive number. Negative infinity does similarly. It extends all the way to the left with a right end that pushes forever farther leftward, eventually passing every negative number. Combining these, we have positive negative infinity, which pushes forever larger both positively and negatively. The basic infinite near numbers are models for special types of what is called divergence because they don't squeeze toward any number in the real line. Our third type of basic near number is the constant near number, obtained by adding a dot to any set in the real line. These don't squeeze at all, but we'll see that they're useful in some circumstances, such as when we discuss indeterminacy. Some of the ones that we'll encounter are 0 infinity dot, which we'll see is the result of multiplying 0 plus times positive infinity. Note that the infinity symbols we use in interval notation simply mean the interval doesn't end. These have nothing to do with motion or near numbers. Negative infinity infinity dot, the whole real line, which we also denote by star for short, is what we get, for example, when we subtract positive infinity from itself. Negative 1, 1 dot, which is the cosine or sine of positive infinity, and the set 0, 1 dot, which comes up, for example, for the divergent series 1, minus 1, plus 1, minus 1, plus 1, minus 1, etc., or the Dirichlet function. The moving pictures we've just seen show almost everything you need to know about the basic near numbers. We'll add just one more detail in order to make them completely rigorous mathematical objects. Near numbers squeeze forever, and this is how we should always think about them. If we freeze that motion at an instant in time, then we see a plain old non-moving set in the real line, which we refer to as a slice of the near number. Here are the details in words. Given any near number alpha, this could be 1 plus, 0 plus minus dot, plus minus infinity, etc. For any positive real number t, we denote the corresponding snapshot of alpha by slice sub t of alpha, which is a set of real numbers. The smaller the value of t, the closer we are to the ideal location the near number represents. When we animate a near number, we're watching what happens as t gets smaller and smaller. Since t is always positive, there's always just a bit farther to go. Now let's make sure we understand that statement by looking at some slices of our basic near numbers. We'll illustrate slices of basic finite near numbers with the example of a plus minus, which looks like this. For any positive t, this is what slice t of a plus minus looks like as a set. Note what t indicates. For basic finite near numbers, t measures the distance to the farthest edge of the slice from the number we're squeezing towards. The smaller t gets, the closer we squeeze. So if t equals 1, we have the slice extending 1 unit left and right from a. If t equals 1/2, it extends just half a unit away. If t equals 1/10, the slice extends just a tenth of a unit away, and so on. There will be such a slice for each positive value t no matter how small, meaning that the near number squeezes forever closer to its limit. To illustrate slices for basic infinite near numbers, let's look at positive negative infinity. For any positive t, this is what slice t of positive negative infinity looks like as a set. Note a little twist here. The measurement on the picture is 1 over t. This is because smaller values of t should get us closer to positive negative infinity. The smaller t gets, the larger 1 over t gets, pushing our slice farther and farther away from 0. For example, when t is 1/10, we have our intervals starting 10 units away from 0. When t is 1/50th, they start 50 units away. Note again how the smaller t pushes the slices farther away. When t equals 1/100th, the intervals start 100 units away, and so on. The smaller t gets, the farther out we push the intervals. Again, there will be such a slice for each positive value t no matter how small, and the slices will thus push forever farther away from 0. Of course, constant near numbers don't squeeze at all, so their slices are all the same with no t in the picture. For example, slice t of 0 infinity dot is simply the interval 0 infinity for every t. The moving pictures of near numbers are all we'll need for most purposes, but slices let us formalize near numbers, which we'll need to do when we talk about definitions and proofs later. That's it for our introduction to the basic near numbers. Everything else we say will build upon these, so learn them well. Next we'll learn how they relate to one another, then how to use functions and arithmetic with them, and finally we'll come to formal proofs of near number statements. Please share this video and check our blog, where we'll announce new videos and discuss questions that come in. And don't hesitate to use the contact email below if you have any questions along the way.